Transformers are not 100% efficient. They typically have an efficiency of 95 to 99%. This means that a small amount of power is lost as heat. When transforming power from 460 volts to 208/120 volts, the amperage will increase. This is because the power in voltamps remains the same. Power in voltamps is equal to voltage in volts multiplied by current in amps. Therefore, if you reduce the voltage by a factor of 2, the current will increase by a factor of 2 to maintain the same power. Voltage drop is the reduction in voltage that occurs when current flows through a wire. As the current increases, the voltage drop also increases. This is because the electrons flowing through the wire collide with the atoms in the wire, which causes resistance. Resistance is a measure of how difficult it is for electrons to flow through a material. The higher the resistance, the greater the voltage drop. Transformer taps are used to adjust the secondary voltage of a transformer. The taps are located in the secondary winding of the transformer. By connecting the output wires to different taps, you can change the number of turns in the secondary winding. This changes the voltage ratio between the primary and secondary windings, and therefore changes the secondary voltage. Taps can be used to compensate for voltage drop. By connecting the output wires to a higher tap, you can increase the secondary voltage. The amp draw of a load will affect the voltage drop. As the amp draw increases, the voltage drop will also increase. This is because the increased current flow causes more collisions between electrons and atoms, which increases the resistance and voltage drop. When an appliance like a range or dryer is turned on, the meter voltage will change. This is because the increased amp draw will cause a voltage drop in the wiring. The voltage drop will be greater when the range and dryer are both running at full load. Electrons are negatively charged particles that orbit the nucleus of an atom. When electrons flow through a wire, they create an electric current. The flow of electrons is called current. The amount of current that flows through a wire depends on the voltage and resistance. Voltage is the force that pushes electrons through a wire. Resistance is the opposition to the flow of electrons. Now let's delve deeper into these concepts. Considering the initial scenario, the choice of running 500 MCM cable for a small building with minimal load might seem excessive. However, several factors could justify this decision. Firstly, future expansion. The government might anticipate future load increases in the building. Installing a large cable initially provides the capacity for future needs without requiring costly upgrades later. Secondly, voltage drop considerations. Over long distances, voltage drop becomes a significant concern. Using a larger conductor like 500 MCM minimizes voltage drop, ensuring that the building receives adequate voltage even at the end of the 8,000-foot run. The initial calculation of 30 amps at 460 volts might be a conservative estimate based on the minimum acceptable voltage at the building. Thirdly, redundancy and reliability. Government installations often prioritize reliability. A larger cable provides a higher safety margin and reduces the risk of overheating or failure. Redundancy might also be a factor, with a larger cable capable of handling a higher load in case of unforeseen circumstances. Regarding transformer efficiency, it's crucial to understand that no transformer is perfectly efficient. A typical efficiency of 95 to 99% means that some energy is lost as heat due to factors like core losses and winding resistance. While this loss is relatively small, it's still a factor to consider, especially in large installations. When stepping down voltage from 460 volts to 208/120 volts, the amperage on the secondary side will increase proportionally to maintain the same power. The power in voltamps, which is calculated by multiplying voltage and current, remains relatively constant, neglecting the small losses due to transformer inefficiency. This relationship is governed by the principle of conservation of energy. Therefore, if the voltage is reduced by a factor of 2, the current will increase by approximately a factor of 2. Now let's explore the concept of voltage drop versus amp draw in more detail. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. This voltage drop is directly proportional to the current flowing through the conductor and the resistance of the conductor. This relationship is described by Ohm's law, which states that voltage is equal to current multiplied by resistance. As the current increases, the voltage drop also increases. This is because the increased flow of electrons through the wire causes more collisions with the atoms in the wire, leading to increased resistance and energy loss in the form of heat. The resistance of a conductor depends on several factors, including the material of the conductor, its length, and its cross-sectional area. Longer conductors have higher resistance, and conductors with smaller cross-sectional areas have higher resistance. Using a larger conductor, such as 500 mcm, reduces the resistance and therefore minimizes voltage drop. The initial calculation of a 3% voltage drop at 30 amps and 460 volts over 8,000 feet using 500 mcm cable indicates the cable's ability to maintain voltage within acceptable limits under light load conditions. However, at 200 amps, the voltage drop increases significantly to approximately 14.9%. This illustrates the nonlinear relationship between current and voltage drop. As the current increases, the voltage drop increases at an accelerating rate. This is because the resistance of the conductor can also increase slightly due to the heating effect of the current. Now, let's discuss how transformer taps work. Transformer taps are used to adjust the secondary voltage of a transformer in order to compensate for voltage drop or to match the voltage requirements of the load. These taps are located on the primary or secondary winding of the transformer, and they allow you to change the turns ratio between the primary and secondary windings. By connecting the input or output wires to different taps, you can effectively change the number of turns in the primary or secondary winding, which alters the voltage ratio and therefore the secondary voltage. For example, if the secondary voltage is slightly low due to voltage drop in the supply conductors, you can increase the secondary voltage by selecting a tap that provides a higher turns ratio. This will boost the secondary voltage and compensate for the voltage drop. However, it's important to note that adjusting the taps will only correct for a fixed amount of voltage drop. The voltage drop in a circuit varies with the load current, so adjusting the taps to compensate for voltage drop at one load level might not be optimal at other load levels. In a residential setting, the voltage at the load center will indeed fluctuate when large appliances like a range and dryer are turned on. This is because the increased amp draw of these appliances causes a voltage drop in the wiring between the service entrance and the load center. The magnitude of the voltage drop will depend on the size of the service conductors, the distance from the service entrance to the load center, and the amount of current drawn by the appliances. To minimize voltage fluctuations, it's important to use adequately sized conductors and to keep the distance between the service entrance and the load center as short as possible. Finally, let's review some basic electron theory. Electrons are negatively charged particles that orbit the nucleus of an atom. These electrons are responsible for carrying electric current through a conductor. When a voltage is applied across a conductor, it creates an electric field that exerts a force on the electrons, causing them to move. This movement of electrons constitutes an electric current. The amount of current that flows through a conductor depends on the voltage applied and the resistance of the conductor. Voltage is the electrical potential difference that drives the flow of electrons, and resistance is the opposition to the flow of electrons. Materials with low resistance, such as copper and aluminum, are good conductors of electricity, while materials with high resistance, such as rubber and glass, are poor conductors of electricity and are used as insulators. In summary, understanding the principles of transformer efficiency, voltage drop, transformer taps, and electron theory is essential for designing and maintaining safe and efficient electrical systems. By carefully considering these factors, it's possible to minimize energy losses, ensure proper voltage levels, and prevent electrical hazards. The choice of conductor size, transformer selection, and wiring practices should all be based on a thorough understanding of these fundamental concepts. This knowledge will enable the creation of reliable and effective electrical installations that meet the needs of the application. Consider also factors like ambient temperature and conductor insulation type when calculating ampacity and voltage drop. Higher ambient temperatures can reduce the ampacity of a conductor, requiring a larger conductor size to carry the same amount of current. The insulation type of the conductor also affects its ampacity rating. The National Electrical Code, or NEC, provides tables and guidelines for determining the appropriate conductor size and insulation type for various applications. For example, NEC Table 310.15b16 provides ampacity ratings for various conductor sizes and insulation types based on an ambient temperature of 30 degrees Celsius. Correction factors are also provided for adjusting the ampacity ratings for different ambient temperatures. When calculating voltage drop, it's important to use the correct formula and to account for all factors that can affect voltage drop, such as conductor length, conductor size, conductor material, and load current. The NEC provides a formula for calculating voltage drop in direct current and alternating current circuits. This formula takes into account the resistance of the conductor and the current flowing through it. It's also important to consider the voltage drop limitation specified in the NEC. The NEC recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. These limitations are intended to ensure that equipment operates properly and to prevent overheating of conductors. In addition to the NEC, there are other standards and guidelines that can be used to design and install electrical systems. These standards and guidelines may be specific to certain industries or applications. It's important to be familiar with all applicable standards and guidelines when working on electrical systems. Furthermore, proper grounding and bonding are crucial for electrical safety. Grounding provides a path for fault current to flow back to the source, which helps to trip circuit breakers and prevent electrical shock hazards. Bonding connects all metal parts of an electrical system together, which helps to equalize voltage potentials and prevent electrical shock hazards. The NEC provides detailed requirements for grounding and bonding electrical systems. These requirements are intended to ensure that electrical systems are safe and reliable. Regular inspection and maintenance are also essential for ensuring the continued safety and reliability of electrical systems. Inspections should be performed by qualified electricians to identify any potential hazards or problems. Maintenance should be performed on a regular basis to prevent equipment failures and to ensure that electrical systems are operating properly. This includes tightening connections, inspecting insulation, and testing circuit breakers. In conclusion, designing, installing, and maintaining electrical systems requires a thorough understanding of electrical principles, codes, and standards. By following these guidelines, it's possible to create safe and efficient electrical installations that meet the needs of the application. Careful planning, proper installation, and regular maintenance are all essential for ensuring the long-term reliability and safety of electrical systems. Consider short-circuit current ratings for equipment. Electrical equipment must be rated to withstand the available short-circuit current at its location. This rating is known as the short-circuit current rating, or SCCR. If the available short-circuit current exceeds the SCCR of the equipment could be damaged or destroyed in the event of a short circuit. The available short-circuit current can be calculated using various methods, including point-to-point calculations and software simulations. The SCCR of equipment is typically marked on the equipment nameplate. It's important to ensure that the SCCR of all equipment is greater than or equal to the available short-circuit current at its location. If the SCCR of the equipment is too low, it may be necessary to install current-limiting devices such as fuses or circuit breakers to reduce the available short-circuit current. Coordination studies. Coordination studies are used to ensure that overcurrent protective devices such as fuses and circuit breakers will operate in a coordinated manner in the event of a fault. The goal of coordination is to isolate the fault to the smallest possible area, minimizing the impact on the rest of the electrical system. Coordination studies involve analyzing the time current characteristics of all overcurrent protective devices in the system to determine how they will respond to different fault currents. The results of the coordination study are used to select the appropriate ratings for the overcurrent protective devices and to adjust their settings to ensure proper coordination. Arc flash hazard analysis. Arc flash is a dangerous electrical phenomenon that can occur when a short circuit or other electrical fault creates an arc of electricity in the air. Arc flash can generate intense heat and pressure, causing severe burns, injuries, and even death. Arc flash hazard analysis is used to assess the risk of arc flash in an electrical system and to determine the appropriate safety measures to protect workers from arc flash hazards. The analysis involves calculating the incident energy and arc flash boundary for various locations in the electrical system. The incident energy is the amount of energy that a worker would be exposed to in the event of an arc flash. The arc flash boundary is the distance from the arc flash source at which the incident energy is equal to 1.2 calories per square centimeter, which is considered the threshold for second-degree burn. The results of the arc flash hazard analysis are used to select the appropriate personal protective equipment, or PPE, for workers and to develop safe work practices for working on or near energized electrical equipment. Power quality. Power quality refers to the characteristics of the electrical power that is supplied to a load. Poor power quality can cause equipment malfunctions, reduce equipment life, and increase energy costs. Common power quality problems include voltage sags, voltage swells, harmonics, and transients. Voltage sags are temporary reductions in voltage that can occur due to motor starting, equipment switching, or faults in the power system. Voltage swells are temporary increases in voltage that can occur due to lightning strikes or switching of large loads. Harmonics are distortions in the sinusoidal waveform of the voltage or current. Transients are short-duration, high-amplitude voltage or current spikes that can be caused by lightning strikes or switching of inductive loads. Power quality monitoring equipment can be used to measure and analyze power quality problems. Power quality mitigation techniques such as surge suppressors, harmonic filters, and voltage regulators can be used to improve power quality. Energy efficiency. Energy efficiency is the practice of using less energy to perform the same task. Improving energy efficiency can reduce energy costs, reduce greenhouse gas emissions, and improve the reliability of electrical systems. There are many ways to improve energy efficiency in electrical systems, including using energy-efficient lighting, using energy-efficient motors, using variable frequency drives, or VFDs, for motor control, improving power factor, and reducing standby power consumption. Energy audits can be used to identify opportunities for improving energy efficiency. Energy-efficient equipment and practices can save significant amounts of energy and money over the lifetime of the equipment. Renewable energy. Renewable energy is energy that comes from sources that are naturally replenished, such as sunlight, wind, and water. Renewable energy sources are sustainable and environmentally friendly. Common renewable energy sources include solar photovoltaic, or PV, wind turbines, hydroelectric power, and biomass. Renewable energy systems can be used to generate electricity, heat water, and provide space heating and cooling. Renewable energy systems can be installed on a small scale, such as on a residential rooftop, or on a large scale, such as a utility-scale solar or wind farm. Renewable energy systems can help to reduce reliance on fossil fuels and to reduce greenhouse gas emissions. Smart grid. Smart grids are electrical grids that use advanced technologies to improve efficiency, reliability, and security. Smart grids use sensors, communications networks, and control systems to monitor and control the flow of electricity. Smart grids can enable two-way communication between utilities and consumers, allowing consumers to manage their energy consumption and to participate in demand response programs. Smart grids can also improve grid reliability by automatically detecting and responding to faults and outages. Smart grids can also integrate renewable energy sources into the grid more effectively. Electrical safety. Electrical safety is paramount when working with electrical systems. It's crucial to follow all safety precautions and to use appropriate personal protective equipment, or PPE, to prevent electrical shock and arc flash injuries. Only qualified electricians should work on electrical systems. Before working on any electrical equipment, it's important to de-energize the equipment and to verify that it is de-energized using a voltage tester. Lockout/tagout procedures should be used to prevent accidental re-energization of the equipment. Rubber gloves, safety glasses, and arc flash suit should be worn when working on or near energized electrical equipment. Never work alone on electrical systems. Always have a qualified person nearby to provide assistance in case of an emergency. Regular safety training is essential for all electrical workers. By following these safety precautions, it's possible to prevent electrical accidents and to ensure a safe working environment. Continuing education. The field of electrical engineering is constantly evolving, with new technologies and standards being developed all the time. It's important for electrical engineers and electricians to stay up to date on the latest advancements in the field by participating in continuing education courses and attending industry conferences. Continuing education can help to improve skills, enhance knowledge, and maintain professional licensure. Many professional organizations, such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA, offer continuing education courses and certifications for electrical professionals. By investing in continuing education, electrical professionals can ensure that they have the knowledge and skills necessary to meet the challenges of the future. It is also recommended to review the newest version of the NEC for any updates and changes.